Assalamu alaikum everyone. I'm Hadia Rashid and I'll be your host for today's conversation. I'm very pleased to be joined by Dr. Mohammad Haris, who is a Pakistani-based scientist in Australia and his recent work is making waves on international media. First of all, a huge congrats to you. It's a pleasure to have you here.
Thank you. Thank you very much, Adia, for inviting us to your platform. And thank you for giving us the opportunity to share our work with the large audience of the people.
Thank you. Okay, so starting with, your team is working on the simultaneous removal of microplastics, nanoplastics, and PFAS, if I'm not pronouncing it wrong. These are quite different types of pollutants. So, what inspired your team to bring them together in one treatment approach?
I think it's a very good question. So when we talk about the pollutants, there are different types and classes of the pollutants, and the types of the pollutant I am talking about, they are categorized usually as emerging pollutants. So um, we can talk about plastics, microplastics differently, and then the PFAS and microfibers. These all sort of pollutants in different researches. But when we see them in the natural environment, they usually coexist. So uh, we started this work in early 2022 with the microplastics, and then because, as I said, that they coexist in the natural environments, and the PFAS is a very problematic pollutant as well, and has a very strict regulations around the world. So we thought that there should be a platform where we can uh, address multiple pollutants at a time rather than addressing them separately. So that was the main motive behind doing this sort of the work.
Okay, so that's amazing. For someone hearing about PFAS for the first time, could you briefly explain what those PFAS are and why they're often referred to as forever chemicals?
Uh, PFAS, they are basically fluorocarbons. It's a class of fluorocarbons. So it's usually carbon fluorine bond, which is uh, thought as one of the strongest bond in the chemistry. So it is very hard to break down in the natural environments, and they are widely have been used because of their exceptional abilities, because they are resistant to the environment, and that is problem as well because they uh, usually don't break down in natural environment. So that's why they are called as forever chemicals. And once they are in the body as well, they are going to be, there as well because they usually don't break down and have been linked with the several severe diseases. So PFAS is just a one class of the fluorocarbons. Basically, it represents a very large group of fluorocarbons.
Okay, so my next question would be like your material has reportedly demonstrated more than 95% removal of micro and nanoplastics within an hour. Could you walk us through what is actually happening when this magnetic absorbent comes into contact with contaminated water?
So when we talk about the microplastics and nanoplastics, so one thing is just to, for the sake of understanding, is the human hair is 10 of thousands of the nanometer of the size. So when we talk about the nano particles, we basically can't see them, and they will be in different sorts of water, and we will not have an idea that they still are there. So the as we go below down the size of microplastics, because they are solid particles, they become very hard to remove from the water because the instead of usually uh, these particles are forced through the membranes to remove, but it is very problematic for the smaller sizes because they usually escape, or they usually the clog the membranes of the and pose these sort of the issues. So we have tested under different circumstances and with the different conditions, and we have showed that it can remove up to 90%. So the main thing is, rather than just removing the 30 nanometer, we have created a platform where we basically absorb those small nanoparticles on our material. And because that material is magnetic, we are just now removing a very big particle out of the water rather than just 30 nanometers. So just bypassing the conventional filtration mechanism. So that is something we have done. And because our material is magnetic, we are just not looking at the removal here. We are looking beyond that, which is the regeneration, reusing it multiple times, and then converting back into another functional material once it has achieved its life.
Okay, so like as you mentioned, is this regeneratable or something like?
Yes, yeah, because it is magnetic. So uh, the powder is magnetic, and once the nanoparticles attach on that one, we just use an external magnet, and that external magnet pulls out the our material which has a pollutant already loaded on top of that. So yes, it is reusable. In the lab, we have shown up to 5 cycles we can reuse the same material multiple times. So we can regenerate and we can reuse it multiple times.
So that powder is made from waste, if I get you correctly.
We started it from the waste, but then to make it more commercially viable, we have now used a carbon source which is more easily available. But you're right, the start of the work was with the waste, but it can work with the number of the carbon precursors. So that's the beauty of the platform we have generated, that we can tweak the properties and we can tweak the raw materials as per our need. But currently, it is not the waste. It is a commercially available carbon material. So that because doing this work was our main idea was to translate into the real world. So we were thinking in a way that so that we can have this our platform developed in a way that can be easily can be synthesized at commercial scale beyond the laboratory.
Wow, that's amazing. So,
Yeah.
one aspect of this research that I find particularly fascinating is the size of particles you are able to capture. So, nanoplastics are often described as invisible pollutants because they are so incredibly small. Why are nanoplastics particularly difficult to remove from waste and from
It's a
water?
very good question, and that is a very problematic at the moment as well to deal with these sort of particles. As I was telling you that because they are very small in size, we
Yeah.
can't see them. So the problem with them is the commercial strategies. They are not capable to capture those ones, these smaller ones. So either they goes into the sludge through which they goes back to the soil, or they go to the water. Uh, because of their size and because they're very active into the water and they are solid particles, it is very hard to capture them. So that is the where the most of the work is now going on through the world, where people are more focusing towards that size to capture that tiny particles so that they are not either going into the our waste streams or not going to the soil.
Okay, so that's something I actually personally want to know that how many people in your team are working like you and how many others?
Yeah, this work was part of my PhD.
Okay.
Um, uh, so we have people of 3 people. Two are my supervisors, and I am the leading researcher on that one. But the recent work is a part of my postdoc work. So you can say that we are 3 people working continuously on the same concept. But now we have expanded team to the approximately 5 people, where we have different researchers from different countries. They are also contributing onto the similar ideas and expanding the objective of our overall work.
Okay. So I think RMI University, Australia.
Yes.
Okay. So moving back, your research was able to capture particles as small as 30 nanometers. What was the key scientific breakthrough that made that possible?
So again, the size of the particles are small. It is hard to design a material which can capture those tiny particles. So if we talk about the scientific innovation in the overall work, the pollutant chemistry is very different for the nanoplastics and the PFAS. So we need a very different properties to remove the PFAS and very different properties to remove the nanoplastics. But in our material, we have developed the properties which can attract the PFAS particles and which can also attract the nanoparticles on the same platform. So the overall concept is the magnetic material rather than just filtering. We are just putting that magnetic particle into the water, which is attracting all the nanoparticles and the PFAS we tested. So now it is very easy to remove that micrometers size of the magnetic particle rather than just removing the nanoparticle. So it is a very convenient process. And because of the magnetism, we can use it multiple times and the separation is very easy. And if we just talk about, for example, the deployment, it is very easy. It can complement, any filtration system or any existing infrastructure where we just mix our adsorbent with the water and we just use external magnet to remove the magnetic particle loaded with all the pollutants, and then just the clean water goes away.
Okay, so as you talk about the conventional water treatment technologies, so how close are we to having a single treatment solution that could realistically tackle both plastic pollution and these forever chemicals like PFAS on a large scale?
I would say it is a promising platform, uh, and it will again complement to the conventional systems. When we talk about to the PFAS, because the PFAS, as I explained to you, is a very large group of uh, you know carbon fluorine particles. So there are numerous particles in that one, but we only have tested one in this case. So possibly our future work will be doing the rest of the PFASs and then developing a platform where we will be basically looking to remove different classes of the PFAS along the nanoplastics. When we talk about the microplastics and the nanoplastics, we have tested very different sizes and the types of the microplastic. So our next, the current one was to develop a lab-based prototype where we can show that this can work in a real-time demonstration. And at the same time, we are working on the cost analysis and the techno-economical analysis, these sort of things, where we are just now targeting that we can scale up the overall process of the material manufacture so that we can translate this from laboratory to the real world. So we are not far, but still there is a lot of work to do before we can have a platform where we can be uh, removing both of them at one time at commercial scale.
Okay, and that's amazing. So, would you see this technology eventually replacing conventional treatment methods, or would it be more realistic to integrate it as one step within an existing treatment system?
Yeah. I wouldn't say it would replace, and I think it shouldn't replace because they both serve very different purposes.
Yeah.
So, because it depends upon the type of the streams, waste streams coming into the water. So, I think that will complement to the existing infrastructure because the technology, the current technologies are not efficient, as I told for the nanoplastic, because either they transfer plastics to the sludge or either it goes to the waste. So I think we can solve that problem where we are capturing that tiny particles so that they are not going into the waste stream. So I would say that it will be a combination of with the other technologies.
Now I would like to bring this discussion closer to Pakistan. Pakistan and many other developing countries are facing challenges around water pollution and wastewater management, often with the limited infrastructure and financial resources. If we were thinking specifically about Pakistan and what would need to happen before a technology like this could actually be deployed in a wastewater treatment plant?
So for the countries, developing countries, especially like Pakistan, the efficiencies of any system is also important, but the cost is also another very important parameter to, you know, the Pakistan is very relevant in this case because the microfibers are also the types of the you can relate to the types of the nanoplastics. The polyester fibers, they basically shed a lot, and Pakistan has a very huge textile sector. So we basically tested a sample from one of the textile sector from the Pakistan as well with our this platform, and we removed the microfibers from their waste as well. So for the Pakistan, if we talk about deploying that technology, I think we will be having uh, this technology at where the waste is very concentrated at first, so that we are removing the particles at source. They are not going into the waste streams as per such as rivers or into the drinking water or into the into the soil. So the best strategy to deploy this sort of the thing is to where you can see a very high pollutant load is coming out. For example, I just gave you the example of the microfibers. So there is a huge microfibers, they come out from the textile sector. So that can be one of the very critical sector where this sort of the technology can be employed. And as our platform, it is very convenient to place in these sort of sectors because we are not replacing anything. We are just adding a very simple step where you don't need any specialized skill, where you don't need any very expensive equipment, where you just can deploy the system, and it can remove the microfibers, and then magnetically the uh, the particle which has the microfibers on the top of that can be recovered and the clean water can go away. So these sort of things I think can be used in case of Pakistan.
Okay, no, if I get you correctly, like if a textile industry is just throwing the waste out of the industry without proper treatment, the industry can use this technique at a source.
100%. Yes. So definitely they can use, and it will reduce the pollution significantly, which is going into the waste streams. That was what I was referring. So we took the waste from one of the textile industry from Pakistan. We didn't took the from the at the very end, but we did take it from the middle of the process where they have the very huge microfiber. So the purpose was to see that because we were working very efficiently in the lab scale into the very smaller size. So we just wanted to have a proof of concept whether it will work with a real sample or not. So that real sample has the different dyes in it as well, and it was a very complex wastewater. So our material demonstrated that it removed more than 90% of the microfibers in the nano range, uh, removed alongside with the dyes from that commercial wastewater from the textile sector.
So your findings are very promising at the research level, but what to happen next? Are you currently looking towards pilot scale trials or commercialization, or probably expanding the technology to target other emerging contaminants in the water?
Yep. I think we are working parallelly in upscaling and at the same time having a platform where we can deal with the multiple pollutants. So just to add the work which I am referring now, it is not only the PFAS and the micro nanoplastics, but it also has the dyes, medicinal waste, and the heavy metals as well alongside the
Okay,
microfibers, such as the mercury. So it was a proof of concept whether to see that we have a platform, a simple question that can we have a platform where a different source of the waste we can remove them from the complex wastewater systems. So I think we answered that one. And the meantime, we are working along with our industry partners and with the different companies on working on the techno-economic analysis and these sort of things so that we can take our technology to the next level. The work we did in 2022 and the work we just did has a significantly leap in terms of the product development, in that we have kept our platform internal mechanism of the material very similar, but we have worked in a way so that the material cost can be significantly reduced and it can be produced at easily at any place. So we are already working towards the commercial scale and the deployment and these sort of things. So, for example, in this work, we used the commercial magnetic separator from one of the company from the Canada to show that this system is work in the commercial setup as well. So I think we are now close to the pilot scale, but still there is some work to do, and we are very hopeful that we can transform our research from laboratory to the commercial systems.
Inshallah, inshallah, surely. Okay, so we've talked a lot about the technology. So I would like to end by talking about the person behind the research. As a Pakistani scientist working on a global environmental challenges, what advice would you give to young Pakistani researchers who want to pursue their careers in environmental engineering and water sustainability?
I think the important thing is the fundamentals are very important, but I wouldn't say limit yourself to one strong particularly thing. So look beyond and try to answer the question, a very simple question, which is very pivotal to the environment or to the people. So just write down a simple question, what you are trying to solve, because to do a very good research you don't need a fancy equipment at start, you don't need a very high tech atmosphere, rather you need a very simple question, that what you are trying to solve, and then you can definitely look beyond and you can talk the people already working in the field, and you just can, because your simple question can be the answer to the one of the global crisis. For example, I just talk about the microfiber. They are very relevant to the Pakistan, but they are not only relevant to the Pakistan, they are very relevant to the global research as well. So just a single problem, and just look beyond and try your capabilities to solve that problems. In my case, I wouldn't say it was only chemical engineering that helped me, but it was the environmental engineering, it was the materials engineering. Then I have worked in the electrochemical systems as well. So these all sort of things basically combine me to give a very different background to answer these sort of the questions. And in this, age of AI and the data science, I think these are very crucial things to adopt and to use in the research to answer these sort of the questions as well.
Okay, so like you're saying that we should expand our horizons and shouldn't limit ourselves to certain things.
Correct.
Okay. So that's very interesting. Before we close, is there anything about microplastics, PFAS, or the future of water treatment that you feel the public needs to understand, but we haven't had the chance to discuss it?
Sorry, can you repeat the question? There was some interruption.
Okay. So I'm asking about, is there anything about microplastics or PFAS or the future of water treatment that you feel the public needs to understand, but we haven't had the chance to discuss it?
I think one thing is very important. What we are trying to do is to solve a problem which we all created. So that is the very end of the tail.
Yeah.
So if we are trying to remove from the drinking water or from the wastewater, it has come from some point, right?
Yeah.
Even if we deploy our resources at the source, there are still the plastics and these sort of chemicals which are generating at very enormous amount. So many of the countries have tried to limit the production or limit the use of the types of these sort of the chemicals or the pollutants. So I think one thing is very important is to limit your use where you can for the single-use plastics. And some things and especially the littering and these sort of the things, they contribute to the huge runoff of the tiny plastics. So I would say a sensible use and the safe disposal of the plastic is a very important thing.
Okay, that's amazing. Thank you so much, Dr. Haris. This has been a really insightful conversation. I wish you and your team the very best for the next stages of this research. Thank you for taking the time to talking with us today. Thank you so much.
Thank you very much. Thank you.
Thank you.